rotation is always happening around us. This is a galaxy that is rotating in the universe through some point, some axis. Oh, this is a planetary system. All the planets are rotating maybe through the sun. This is the Earth, that it rotates around its axis. And from the big objects rotating, we can see a small object. This is an atom with the electrons rotating in certain orbits. Oh, and normal objects like a wheel that is rotating, or maybe a point that is rotating through some point that is the center, or maybe just your chair is rotating. Rotation is happening all over, all around you. Look at this car moving at constant speed. Magnitude of the velocity constant through a circle of radius r from the center. This radius, well, I don't see the radius, okay, but he's moving in a circle. Now see the vector velocity at 4 instants of time. Here is the vector velocity v. Now is the vector velocity v. Now it will come the vector velocity v. Of course, there is another vector velocity meanwhile, and here there is a vector velocity v. So the vector velocity is changing its direction all the time. In this case of circular motion, the magnitude of the vector velocity is not changing. Now to calculate this acceleration that is called centripetal acceleration, going to the center. To calculate, we need to know the speed of the object that is moving around the circle, and we need to know the radius of the circle. Also, we want to know in what direction will be the acceleration. But we know the direction of the acceleration. The direction of the acceleration is always the same direction as the direction of the change in v. So the acceleration have this direction, the same direction as the change in v. Or if you prefer the change in v, follow the vector acceleration, because this is an scalar. This will make the a to be bigger. So if we find to where it will go the change in the velocity, we'll know in what direction will be the acceleration. Let's go to work this. This is a wheel that is rotating. The arrow that you see is the vector velocity. Is rotating through this axis, through the axis in the center. This is the vector velocity, and as you can see, the vector velocity is changing continuously. And even the magnitude of the vector velocity is not changing, but the direction of the vector velocity is changing. So this change in the direction of the vector velocity will produce acceleration. And the acceleration in this case, where the velocity is constant, what it means that this velocity is constant? That the magnitude of the velocity, the length of the arrow, is not changing, is always the same length of the arrow. So we are going to deduce an equation to measure the acceleration of this motion. And of course, this motion is uniform circular motion. Motion where the magnitude of the velocity doesn't change, but of course if it's a circular motion, the direction of the velocity is continuously changing. Now we are seeing a snapshot of the object rotating in a circular motion at two different times. At the initial time t1, the object is here. The magnitude of the velocity is not changing, it's the same magnitude of the velocity. The object is performing a circular motion. The radius r is maintained constant because if it's a circular motion, this radius will maintain constant. During the time t1 and t2, the object will move and will displace a distance that we will call delta s. Delta s is the arc of distance through the line of the circle. Meanwhile he's doing that, the angle that is swept is delta theta. So he moved from here to here in the time from t1 to t2. He performed this angle delta theta. The velocity changes in direction but doesn't change in magnitude. So the magnitude of the velocity is the distance through the circumference, through the circular motion, the distance divided by the time elapsed, t2 minus t1. So the magnitude of the velocity is what we call the speed. So delta S will be the V by delta T. Now, delta S is this arc, and this arc is the radius by the angle. The radius by the angle is the arc. Why? Because you know that in a circumference, the length of the arc, the angle here and the radius r are related because L is equal R by theta, being theta in radians. This equation is only valid if you measure theta in radians. So if you have a big length, L, that goes around the whole circle, and you have the radius r, the angle that you have is 2 pi. So if you apply this equation, for the big length, let's go to call it capital L, will be r by the angle, 2 pi. Oh, this is the length of a circle. The length is 2 pi r. So this equation is an equation that you need to remember always, and it says that the length of the arc is related with the radius and with the angle by L equal R by theta. Let's go now to see how we will produce the equation for the acceleration. Will be the normal acceleration. Normal means the centripetal acceleration. Centripetal acceleration means going to the center, going to here. We will see that this acceleration is going to the center. It's going to the center. Wherever is the object, the acceleration will go to the center. So at any instance, we will find the velocity going through here, constant, the acceleration going to here, and the position will be going to here. This is the vector position. So clearly the vector position and the vector r are opposite. Okay, let's go to make the calculation. So the vector v is always perpendicular to the vector r. This is something that we have to pay attention. So see this figure. During the time t2 minus t1, during this interval of time, the vector velocity have not changed, but it has displaced this quantity delta s. Delta s is here, and delta s is r by delta theta. Perfect. The magnitude of the velocity is delta s divided by delta t. Perfect. Now see these two triangles that are the basic thing to understand how we make the calculation. This is the initial velocity. This is the final velocity, this one. Where is the change? Here. The change in the vector velocity is from the head of the initial vector to the head of the final vector. This is the vector change in velocity. To where it will go the acceleration in the direction to the change in velocity. Perfect. Perfect. Now see this picture. You see this is r. This is r, the same r that is here, and this is the angle delta theta that is the same angle that this angle delta theta. Why? Because the vector velocity is perpendicular to r. The vector velocity is perpendicular to r. So when the object moves an angle delta theta, is because the two vectors, between them, there is the same angle delta theta. Now we have two isosceles triangles. This is R and R. This is V and V. And they are congruents. So delta V divided by V will be equal to the magnitude of delta R divided by R. So the magnitude of delta R divided by R will be equal to the magnitude of delta V divided by the magnitude of V, because they are two isosceles triangles. But the magnitude of delta R looks like delta S if the time delta t goes to zero, goes if the interval of time is very small, delta S and delta R, what is delta R? Delta R is the vector that goes from the initial R from the head of the initial R to the head of the final R position. So this is delta R. You see that the length of this vector delta R will be delta S if the time is very small. So as delta t goes to zero, delta R looks similar to delta S. Okay. So the equation that I will write will be, instead of writing the magnitude of delta R, I will write delta S divided by R equal delta V divided by V. But delta S is V by delta T. So V by delta T divided by R will be delta V divided by V. But delta V divided by delta T is the magnitude of the acceleration. So delta V divided by delta T is the magnitude of the acceleration. And what it will be if you put this here, if you put delta T here, and you put this V here, it will be V by V divided by R. Okay, so the acceleration is V squared divided by R. And the direction of the acceleration is in the direction of delta V. But the direction of delta V will be exactly in the same direction, in the opposite direction, as is the vector r. So we can write this equation. The acceleration have a magnitude, v squared divided by the radius, and have the direction of where the vector r is. Remember that this means unitary vector in the direction of r, but in the negative direction of r, going to the center. So this is called centripetal acceleration. It's also named normal acceleration because it's going perpendicular, normal acceleration because it's going perpendicular to the tangent. It's going here like this. The acceleration is normal, A. Always A. So we have a situation where the position is like this, the velocity is like this, and the acceleration is like this. When the object is here, the position is like this, the velocity is like this, didn't change, and the acceleration is like this, and so on. Then the two equations that we have obtain are that the magnitude of the acceleration is the magnitude of the velocity squared divided by the radius, positive quantities. This is a positive quantity, this is a positive quantity, this is the radius is a positive quantity. But the vector acceleration is with this magnitude in the direction negative to the direction of the vector r. This is the question that we have deduced. Finalize, we can imagine to solve an example. Imagine that you have a satellite that is orbiting at the radius r from the Earth, 8,000 kilometers around the Earth, and the motion is a circular motion, and the satellite is performing a perfect circle around the Earth. And suppose that the acceleration is a little bit smaller than the magnitude of the acceleration, it's a little bit smaller than at the surface, let's say 8 meters per second square. This value is constant over the circle. But indeed, the acceleration is not constant because the acceleration is always in the acceleration that the Earth is doing on this orbit at 8,000 kilometers is going in this direction, is going to the center, is going to the center, is going to the center. This is a gravitational acceleration, so the acceleration, even if the magnitude of the acceleration is constant, the vector acceleration is not constant. So the question is, what is the velocity of the object that is performing? What is the magnitude of the velocity of the object that is performing the motion, the circular motion? Well, to do that, we can say, if the object is performing a circular motion, the acceleration is v squared divided by r, by the radius. The velocity, the magnitude of the velocity is not changing, but it has acceleration, and the acceleration produced that the direction of the velocity is changing. So in this case, the radius is 8,000 kilometers, the acceleration is 8 meters per second square, going to the center of the radius. So imagine this is the initial velocity, this is the final velocity, and the acceleration is going to the center, so the relation will say that the v squared, the magnitude of the velocity, is equal a by r, so this will produce v squared will be a 8 meters per second by r, will be 64 10 a la 6. B will be a square root of this, so v will be a square root of r by a. In the case that we name the acceleration by g, the equation will be that v will be the square root of r by j. And making calculation, we will have at this problem that the velocity is like 8,000 meters per second. A plane is traveling at 1,000 meters per second. So the satellite is traveling 8 times at bigger velocity, at bigger speed than what a plane is moving. Okay, that's all. Let's go to the summary. The summary says that the circular motion is happening around us at all scale, at the microscopical scale, at the big scale. And the important thing is that circular motion is an accelerated motion. Even if the object is at constant speed, the motion is with acceleration. So the acceleration in a circular motion in the case of the object moving with, in the case of uniform circular motion, where the object is moving at constant speed, the acceleration is v squared divided by r, and the vector acceleration is v squared divided by r in the direction of r, in the minus direction of r, and that's all.